So this is going to be an introduction to differential geometry. It's not going to be a very uh, detailed treatment of theory. I'm not going to give proof of all the claims and elaborate on every single detail, but I just want to give an overview of the basic notions. So if you're not familiar with them in any proper detail, you'll be able to follow along with the spin geometry book. And so I'll remain formal, but I won't prove some claims. I'll leave the proofs up to you. Though, similarly as with the multilinear algebra talk, most of the claims, unless they're explicitly large theorems, are pretty straightforward to show. So in that case, let's get started. And really, as the starting point to this talk, I want to talk about the motivation for differential geometry, kind of what we're trying to do. And of course, it's a subjective thing what you want to do, but one way you can view what differential geometry aims to do is to extend analysis, the usual tools of differentiation, integration, etc., from just finite dimensional Euclidean spaces, Rn, to sort of a broader class of spaces. Now, throughout the talk, I'll be talking of quote-unquote spaces, and until I'll define manifolds, it will just be an ambiguous term. You can just think of sets. Don't really impose any more structure. You could impose topological structure and talk of topological spaces, which is something which I will not do in this talk, though of course it follows, which I'll get in a moment. So for our intents and purposes, we can just take spaces to mean sets. And I will not assume that you're familiar with topological notions except continuity and such, though it is helpful. So some situations in which we might want to do analysis that aren't just strictly Rn, at least not directly. Let's say if we want to consider matrices, specifically invertible matrices, because matrices as a whole, we have just n by n real numbers that give us a matrix, at least if it's a real matrix. It's just the same thing as an element of high-dimensional Euclidean space. Another example would be something like spheres. They are fairly geometrical. You can have an intuition that you should be able to regard them locally as linear objects. And that's really what analysis is about, is locally linearizing situations. And so, again, this is not immediately clear how one should do. There are various approaches. It's not a highly complicated issue to solve, but nonetheless, this is something to investigate, and that's what we do in differential geometry. So the starting point to what one usually does in differential geometry is this remark about classical analysis. If we have some function between Euclidean spaces, throughout the talk, Euclidean spaces, finite dimensional Euclidean spaces also mean just Rn for some natural number n. Then it is absolutely differential at a point P, or really we could replace this with a number of conditions. Absolutely differential with some derivative D. Here by absolutely differentiable, I mean it has a matrix derivative, a Jacobian. So a best linear approximation of the graph, so to say, at the point corresponding to P. This is true for our function f, precisely when it's true to the restriction of f to some ball around P, some small set around P. I mean, visually, this is pretty clear to see. We can imagine the situation drawn as R to R, but of course, these could be arbitrarily dimensional spaces. We have this graph of our function, and this blue line represents the tangent space, the tangent line, tangent plane, etc., to the graph, and its slope is the absolute derivative, or in high dimensions is like matrix of slopes is the absolute derivative. And we know that if you restrict the graph to just a smaller kind of subgraph, where we take a portion of the graph corresponding to all the points in this ball around P, if we look at the tangent to that, it will be just a part of our curve, kind of strictly containing the point corresponding to P, and the tangent is going to agree. And so that the slopes will agree, and it's the same question whether the derivative exists of f or if it's restriction. So in this way, we kind of, any analysis we wish to do globally over all of Rn can reduce that to just doing it locally at small neighborhood reference points. So, well,
probably one moment.
Yes, a question.
What are you doing with that? Like, what is the green interval?
So the green interval here, I mean, as drawn an interval, it's the open ball around P. So we take some small set, it's this B, all the points closer than some epsilon a positive real number, to p. So for example, if you would imagine we consider the, I don't know, identity map R2 to R2, every point maps itself, then if we consider as p the origin, we could take the open unit ball of radius 1, all the points which are 1, less than 1 in norm. So that's what this is. And that's kind of just a small neighborhood around p, all the points sufficiently close to p. I'm just saying that it suffices to consider things locally to do analysis. Analysis is a
Got
good
it.
local
Yep.
thing. Because, I mean, by definition, analysis is about local linearization. You want to find the locally best linear object of fit, locally best line of fit, plane of fit, etc. Tangent space of fit, so to say. And so thus we can just restrict our attention to this b. And of course, here is drawn as an interval, but if labeled the axis Rn, really this is supposed to represent some open ball around a point in the Euclidean space. So this could just as well be a plane as your input axis, and then you'd have kind of this disk, this open disk. Yes, that's what b is. So one way to capture this notion of local analysis, or really at least the kind of intrinsic local analytic structure, analytic not in the sense of power series, just analysis, is that of a pseudo group, and it's a fairly abstract notion that you don't come across in every differential geometry text, but I do think that it's a rather useful tool to express a broad set of definitions as just one definition. So there are many variants of kind of the spaces to do analysis on. So in differential geometry, the spaces we replace Rn with to do analysis on are referred to as differentiable manifolds. And then usually there are various versions of those. We will mostly concern ourselves with smooth manifolds, and I'll get to all of that in a moment. But so these various versions of manifolds, you have complex manifolds, smooth manifolds, ZK manifolds for K some finite natural number, or you could have Lipschitz manifolds or piecewise linear manifolds. Really, this all is part of one definition. It just depends on the choice of what local analytic structure in Euclidean space you choose. So kind of what sort of analysis you're interested in. And really, before I give this definition, I also want to remark that there is a nicer variant of this definition that nobody really uses in literature that allows to formulate more definitions nicely. But I've just went with what is customary. It's just what people use. So that's the notion of a pseudogroup, and specifically a d-dimensional Euclidean pseudogroup. So d-dimensional Euclidean, I just mean on RD in general, you can replace this with some topological space. So again, you don't need to know what topological spaces are to follow this talk. What a d-dimensional Euclidean pseudogroup P consists of is specifications of the types of functions that concern us. Specifically, because we care about the intrinsic kind of analytic structure, we only need to specify the sort of symmetries that this brings with itself. So formally, those will be the continuous, so this pseudogroup P will consist of choosing sets of continuous bijective maps between any two open subsets of RD, U and V, such that there are some properties that hold. And really, they're just kind of very, if you've seen group theory, which I suppose you have in order to follow along this talk in geometries in general, they're very reminiscent of the sort of symmetry conditions you have, because, well, this is kind of supposed to mention, to capture what the analytical symmetry of Euclidean space is. And so we wish that if we have a P kind of function, type P, class P function from U to V, so in this set, then its inverse is 1 from V to U. If we compose two type P functions, class P functions, there are different ways of people calling that, we also get 1. And also, these functions behave well with respect to coverings. So here, I'll mention this in a moment, an open subset of RD is just an arbitrary union of open balls. And this is just kind of a convenient notion to use. And if we have any family of open subsets for D, whose union is some other open subset, then we wish to have class B functions out of the union to some open subset V to be specifically exactly specified by the restrictions to the sets whose union gives us this whole union to the family of open subsets. So this is a two ways implication. we wish that if we have a restriction of a class B function to an open set, we also get a class B function. That this follows from this if you simply take an appropriate open cover. And vice versa. If we have a bunch of open sets and we have agreeing class B functions on them to some fixed open set V, then we can glue them together. This is kind of a sheaf-like property. And there are much more abstract ways of capturing this, but this is essentially the one that's most elementary. And as mentioned, the alternative version of this definition would be that of a pseudo-monoid. Well, I've not mentioned the name, but this is what it is. And the only difference would be that we don't require bijectivity, and so we get kind of a more broad notion that doesn't only capture kind of symmetries, but the whole analysis itself. And that, because of that, is slightly more useful, but people aren't really accustomed to using that. I'm not familiar with the reasons, but this is just the usual definition. So some examples we can take. If we consider some natural number k, or k is infinity, then a function from an open subset of Rd to another open subset of Rd can be k times continuously differentiable. This is something I'll assume you're familiar with out of classical analysis. It just means that all the partial derivatives whose indices, so if you take a partial derivative with respect to various variables multiple times and the indices sum up to a number no greater than k, then this derivative exists and is a continuous function. And if we wish to consider this as a pseudogroup, we'll simply set our class ck functions from u to v to be those which are bijective, ck, so k times continuously differentiable, and have a k times continuously differentiable inverse. It's not in general true that if you have a k times continuously differentiable function, its inverse is also k times continuously differentiable, something to be checked. So that's one common example of a pseudogroup. And indeed, ck manifolds later will be something that are quite common to look at. Something else you can do, you can identify d-dimensional complex space, so just CD, so the set of all ordered pairs of d complex numbers with R to d, simply identifying one complex number with the ordered pair of its real and imaginary components. You can identify C with R2, and then just kind of, by properties of exponents, identify CD with R to d. And so we can apply our definition of a Euclidean pseudogroup, 2D-dimensional Euclidean pseudogroup if we wish to consider CD. And as our functions, consider those maps which are bijective and holomorphic. So holomorphic, for those not familiar with complex analysis, is just the complex analog of complexly differentiable. So just the same limit definition, except you take the limit inside the complex numbers. And this behaves quite differently and has, in fact, nicer properties. I will not, so in my description of the talk, I wrote that I'll talk about complex manifolds. I mean, really, this is more or less the extent of me talking about complex manifolds. Really, the reason I wanted to include this in here is, first of all, to illustrate that there's a broader theory that can be viewed as part of differential geometry, and also just for the purposes of the book, there will be moments where just kind of being comfortable with the notion of a complex manifold is useful, though we won't need the more intricate theory, I don't believe. At least not to an extent that isn't developed in the book. So in this example, again, we take CD, and we can apply this definition just by taking subset of CD in correspondence with subset of R to D. And then as our functions between open subset U and V, we just take the bijective holomorphic maps. And in fact, you can prove as a fact of complex analysis, novel reason why holomorphic maps are sometimes superior, at least they have nicer properties than just smooth maps. The inverse of the bijective holomorphic map is necessarily holomorphic itself, so we don't need to require the condition of the inverse. But we won't see this in detail. This is just a useful example to be familiar with. So we can take an example, or at least if we wish to conduct now analysis on P analysis. So we fixed our pseudogroup P, D-dimensional pseudogroup that specifies us what kind of analysis we wish to conduct. Now, let's say we wish to conduct P analysis on some space X. Again, for us, we can just say set X. Now, one way we would want to do this, at least given our remark at the beginning, is that if we can think of every single point of X, or if it's a such as an element, I'll use the words interchangeably for this talk. If we can think of any such point as lying inside the space, the same way a point of Euclidean space lies inside Euclidean space, then if we can do this for every single point, we can, by the remark at the beginning, try to translate analysis from the real RD case to our space X. Now, what do I mean by this specifically? I think it's perhaps best illustrated with this example. Let's consider this circle, and this is sort of messy notation, but on the next slide will be a picture illustrating it. If you consider the circle in R2, so all the points of distance exactly 1 to the origin, then we have the two projections, which take a point x, y of R2 and map it to x and y respectively. And we can take the pre-images of the positive reals, the negative reals on each of these projections, yielding us 2 times 2, 4 subsets of the unit circle if you restrict our projections to the unit circle. Now, visually, this looks like this. So if we take the pre-image of the positive real line and the positive reals and the second projection, we'll get this top subset I drew here in blue, y plus is what I call it, and then y minus if you take the negative reals, etc. with x minus x plus. And you can note that every single point in the unit circle belongs to at least one of the circles. We can get away, actually, before I say that, the point of doing this is that each of these arcs can be put in continuous projection, or just projection for all purposes, with the open unit interval, actually this should be the closed unit interval from, open is correct. The open unit interval from -1 to 1. Specifically, if we take a projection onto the x-axis of y plus, say, then we know that any point there will correspond exactly to one point on the x-axis. So we can think of all of these subsets, of these arcs, as kind of copies of the unit interval, the open unit interval, not the unit, I guess the length 2 interval, should we call this the unit interval, the length 2, or the open unit interval from -1 to 1. And the useful thing about this is that now any point on the circle we can think of as lying inside of one of these subsets, just kind of lying inside a copy of the open unit interval, can't stop saying unit, the open interval from -1 to 1. And so we know how to do analysis on the open interval from -1 to 1. We might try to translate it to the subsets. We have to be careful about compatibility because one point might be in separate, multiple subsets rather. So in general, we could cover the n-dimensional sphere with 2n plus 2 sets like this. It'll just be hemispheres if we take the pre-images of projections, and everything works out the same. And again, these hemispheres, they're kind of open unit balls in Rn. And so again, any point in the sphere this way we can think of as a point in a copy of something which is in Rn, and just can try to do analysis on the spheres by moving the situation to these open unit balls in Rn, to the kind of thinking about the points as lying in copies of this. So again, this is still kind of vague, but I'll get to formalizing this in a moment. So this is essentially what I've said here. I also mentioned here that if we say want to think of now differentiable map from S1 to R, we could simply say that for map to be differentiable, we have these bijections with our arcs and the interval from -1 to 1. For a map from S1 to R to be differentiable, we could say that all the compositions have to be differentiable, thinking of the bijection as just identification. The differentiability of the composition is just a question of a function from the interval from -1 to 1 to R. That's a classical question. You can just use the usual definition, the limit, or linear approximation, whichever you prefer. And this way we can get a notion of differentiability in the unit circle by, again, covering these copies of something Euclidean. And so this motivates this rather, at first sight, lengthy but actually pretty intuitive definition. What we can think of is that the terminology is as follows. We imagine these bits that we cover our set with as kind of ways of viewing bits of our set as flat parts of, or just flat subsets of Euclidean space, or just subsets of Euclidean space. And we can kind of think of this as going out into England or just some land and taking bits of that and mapping it into a map and drawing kind of flat copies of that. And so because of this analogy, the usual terminology for these subsets, together with projections to open subsets of Euclidean space at charts. So formally, if we have a set X, and again we fix some d-dimensional Euclidean pseudogroup P, then a P chart on X, or actually we don't need a P here, just a chart on X, is any pair of an open subset of, or not open, just a subset of X. We don't need any notion of openness in X, and a bijection from this subset to some open subset of RD. This is what the openness comes in. So in this way, we have this abstract set X, and we take some part of it, some subset U, and identify that bijectively with an open subset of some fine-dimensional Euclidean space. Now, where the pseudogroup becomes relevant is when we require that the whole set X be covered by such charts, in the sense that every point in X lies in some underlying set of one of these charts. And we require not only that, but also that when the charts intersect, we get these sort of transition maps, and we require the tail AMP. Okay, I didn't quite put this nicely, let me repeat. So we have this notion of a chart, which is some subset of our set together with a bijection to an open subset of fine-dimensional Euclidean space with a fixed dimension. Now, if we have a collection of such charts, such that the underlying sets of them, so these U's cover our set X, so every point is covered by some chart, then this collection will be called an atlas, a P-atlas, provided that we have some compatibility. Because two charts, they may intersect, and then we have kind of two identifications with fine-dimensional Euclidean space with open subsets of that. And we wish to verify that these identifications, they are compatible with regards to our desired choice of analysis. So formally, what we require, and there'll be a visualization on the next page, is that if we have two charts, then when we consider the intersection of the underlying sets and consider these maps associated to the charts, so the terminology is that the inverses of these maps are called local parameterizations. So if we have a chart U phi, then the inverse of phi, so the map from an open subset of RD to U, a bijective map, is called the local parameterization of our set X with the P-atlas. And the maps themselves are called, well, they're not quite called coordinate maps, but sometimes I'm usually called coordinate maps. Coordinate maps are decompositions with projections RD to R. So either way, in verifying that we don't have undesired intersections, incompatibility between the charts, we require that for the collection of charts to be a P-atlas, given any two, if we first go via the local parameterization of one into the intersection of them, and then use the coordinate maps on the other, the resulting map is of class P. Because the resulting map will be a map between open subsets of Euclidean space, the pre-image of the local polarization of the intersection of one of the charts, and then the image of the coordinate maps of the other. And so this map from an open subset of RD to RD, we wish to be compatible with the analysis for our choice. So we wish to be of class P. So in P UV, where U and V are our sets, U and V not the same as in the dice here. So yes, the terminology is that we have these charts, which are these kind of local trivializations of our set. An atlas is a collection of those, such that it covers everything, and such that they're compatible. So it's a P-atlas, and they need to be compatible such that the transition maps, which are these maps which we get if we first go to one of them and then back to the other, from Euclidean space to Euclidean space, those are of class P. The inverses of the maps we have on the charts are the local parameterizations. The maps themselves, by use of terminology called coordinate maps, so really the coordinate maps are the positions of those with the projections RD to R. So what that means is we have this subset of X, and we kind of make it locally, we kind of make that flat by some map. And so it lives now in RD, and if we consider the projections, they kind of get coordinates on this U, and those will be the coordinate maps. This condition we put on two charts to kind of be compatible regarding P analysis, so to say, is called p-compatibility. So if p is, for example, the C-infinity pseudogroup, this will be called smoothly compatible charts. And lastly, a p-manifold is any set and a maximal p-atlas. Now, the reason why we need to choose a maximal p-atlas and what maximal means is that otherwise it might not be obvious if we've missed out on some structure that arises out of our charts. It's also somewhat technical. But so what maximal actually means is that, well, obviously, atlases are collections of sets, so one can be contained in another, or multi-collections of charts. And maximal just means that it is a p-atlas is maximal if it is not properly contained in any other p-atlas in the set. And actually, this is really a mostly technical detail because using some abstract nonsense things, you can verify that any p-atlas uniquely extends to maximal p-atlas. So really, it just for specifying a p-manifold, it suffices to just specify one p-atlas, so one way of covering the set by charts such that they are p-compatible, pairwise p-compatible. So some terminology, actually first, very important visualization. So this is what actually looks like, this is what I was describing. We have our set X, and we have two charts, U and V. And U and V, they consist of some subsets of X. And again, X here is just an abstract set. We don't require any structure. All structure falls from our p-atlas. We have these two sets. They have an intersection. It might be empty, but let's visualize it as being non-empty. And we have these local parameterizations and coordinate maps. So we have the local parameterization of U with some subset VU of Rn. Well, it should be RD, I guess, if we are going with the terminology of the previous page, but just some Euclidean space, open subset VU of Euclidean space. So this is a projection from VU to U. And we have the same on V. If we consider the coordinate map from V to some VV, also in Rn. And if we take the intersection and take its pre-image in the local parameterization, so perhaps let me use my cursor. So we have this intersection and the local parameterization of U. If we take the pre-image, we kind of pull it back to a VU, we have an open subset here. And this is something we require. We require the subset to be open. So the pre-image of the intersection under any local parameterization to be open. Then we have this open subset here, and we can first apply this function. We run an intersection, but in the intersection is contained inside V, so we can apply the coordinate maps there, the inverse of the local parameterization. And we land in some subset of the flat version of V. And so we get this kind of total map. This is called the transition map. And what it requires is transition map to be of class B. This is precisely the definition of what it means for these two charts to be p-compatible. And then atlas is just a cover of X. So imagine we have X here, we just cover it with a bunch of these sort of spots, these subsets, such that they're all p-compatible with each other. And then the p-manifold is any set with a maximal such p-atlas, so it suffices to specify one, and then it extends uniquely. So that's kind of the basis for the manifold is. Essentially, we say we have some set, and we locally can view it as open subsets in Euclidean space. And then because we know how to do analysis on open subsets of Euclidean space, we will be able to do it on X. This is what talk will be about. So some terminology. For the rest of this talk, I will mostly talk about this smooth manifold, smooth real manifold. Real is usually omitted, unless you want a specific context where it matters. It is just a C-infinity manifold, where C-infinity is the pseudogroup of infinitely differentiable functions on some RD, as discussed in the previous example. Now, the pseudogroup is always fixed to some dimension, and then the dimension will be a dimension which the pseudogroup is fixed to will be called the dimension of the manifold. And one will say if the dimension of the manifold is D, that the manifold is a D manifold. In this case, a smooth real D manifold, because it's our pseudogroup smooth real. Now, we can also do this for complex manifolds, and there the canonical pseudogroup of choice is the holomorphic maps. There's not really many alternatives. You could also do piecewise linear things, but really holomorphic map is the usual one. And a complex manifold is just a O manifold, where O is the pseudogroup of holomorphic maps. So in this case, we take some set, we cover it by these subsets together with bijective identifications with open subsets of CD, such that the transition maps, if we start in CD, go to the manifold and go back to CD, those are holomorphic. And again, we have a dimension here. This is the complex dimension of the manifold. So you have to be kind of careful here because, well, if you think of the complex numbers, they will be C1, so a one-dimensional complex manifold over itself. You can take the chart, which contains as the underlying set of the chart, the whole complex numbers, and as the coordinate maps, just the identity function. And so it's one-dimensional because it goes to C1. We kind of by definition define dimension to be this exponent in C, if we're talking about the complex dimension. But of course, if we think of C as R2, the dimension of C is not 1, it's 2. So in fact, well, actually, this will be on the next slide, but a complex d-dimensional manifold is a smooth real 2D manifold. But yes, some more terminology. One and two-dimensional manifolds, one usually refers to as curves and surfaces. So if it's smooth real manifold, smooth real curve, smooth real surfaces. And then for high-dimensional things, there aren't really fixed terminology. You can call three-dimensional manifolds free manifolds or free folds for short, and four-dimensional manifolds as four folds, then five folds, etc. Just kind of short thing, n manifold. And then for complex manifolds, you do the same. You call it a complex threefold, etc. Except because of historical reasons, a one-dimensional complex manifold one calls a Riemann surface. Again, it's a curve because it's one-dimensional if you regard it as a complex manifold. But if you think of it as a real manifold, then any complex manifold is a smooth real manifold of double dimension. Then curves over C become surfaces over R, and so it's a Riemann surface. And that's kind of a lot of where the theory came from with Riemann in the middle of the 19th century. So yeah, my remark, any complex D manifold is a smooth real 2D manifold because CD is just R2D. And so we have when we have a identification of subsets of our set with open sets in CD, we have one with open subsets of 2D, of R2D, and being holomorphically compatible implies being smoothly compatible, because if you think of CD as R2D, holomorphic maps are actually smooth, which is actually one of the very nice properties of holomorphic maps. In fact, really there's kind of a stronger claim that can be made here. It's about comparisons between different pseudogroups. If one pseudogroup, let's call it P, is contained in a pseudogroup P prime, so any function that is of class P is of class P prime. For example, smooth maps are holomorphic. That any P prime atlas will be a P atlas. And so we can import notions from P manifolds to P prime manifolds. For example, if I have something for smooth manifolds, I will have it for complex manifolds. And actually, this will be at times useful in the talk just to keep in your head. For example, I can always talk about continuous maps, or I could talk about, well, I've not introduced really any notions of manifolds yet, but I can talk about anything. I can talk for C1 manifolds, for C2 manifolds, because any C2 manifold is C1 manifold just because C2 maps are C1. Just kind of trivialities, but it's something which impacts the way you organize information here. So yeah, actually an example of a manifold, the first one in this talk, the one essentially I gave before, except in greater generality. Earlier I mentioned CD, it's a complex manifold of dimension D. Just take, or actually I mentioned C, but it works the same way with CD, or actually RD. Just take one chart. So I've talked here about the carbohydrates meet underlying sets. So you take this one set, the whole of RD, and it's already an open subset of RD, so you can just take the identity function from RD to RD, and it is then a chart, a smooth chart. Why is it smooth? Well, if I first go via, so I have to verify the compatibility of my chart with itself, which will always be true because the composition will always be the identity. But why is it identity? Well, if I first go via the identity from RD to RD and then back, well, I've applied the function then in syllabus, I get the identity. So I guess it's not always true, but it's true if the pseudogroup contains the identity maps. So that's one example of manifold. Of course, it's a very boring example of manifold in the sense that it doesn't really give us anything new. Our whole idea here is to extend analysis from RD, but here we just back that RD. But we can do more. This just verifies that everything we've had in RD transfers over. So this is a generalization. So we can use CD as a complex D manifold, just via the same way, because CD we can think of as a 2D. Now a less trivial example is any graph of a function Rn to Rm, a smooth function Rn to Rm. Oh yeah, actually, I forgot to mention that. I'll have to fix it in the slide later. This should be a smooth function, of course. Otherwise, graph function can be completely wild. So if I have a smooth function from Rn to Rm, then this graph is just a set of pairs x f of x in Rn times Rm, which is just Rn plus m. And this can be given a smooth n-fold structure just by considering this one chart, again, one chart for whole atlas, smooth atlas, which has as its unlike set the whole set, and as the coordinate maps just the projections. So we think of the coordinates in our graph, literally the coordinates when we project down onto the Rn below. And this is then a smooth N manifold because we can verify that if we do the composition, we get a smooth map. So a more interesting example of maps yet is that of Sn, the n-sphere, because as mentioned, we can cover Sn with 2n plus 2 open sets, and again, use projections onto the hyperplanes in Rn plus 1 to identify these hemispheres with open unit balls in Rn. And you can verify that, again, if you do the compositions. I mean, a lot of in this talk requires some tedious verification. It's kind of the way the terminology is set up in differential geometry. But you can verify if you use one of the charts we set up for Sn to go from the unit open ball in Rn to Sn, and then use another to go back to the open unit ball, the composite map will be smooth. You can do an explicit computation. I mean, it won't be a very complicated computation. I think you'll get something like a permutation of the coordinates. And so that's another example of a smooth N manifold. Again, why is this a smooth N manifold? Our definition of a smooth N manifold was that of a set with a maximal smooth atlas of n-dimensional open subsets of, or just of open subset of Rn. But any smooth atlas can be extended to a maximal one, so we really don't have to worry about it. It really just suffices to give a manifold to give one atlas. So this is another exemplification of manifolds. So here we already see some structure. We have the theory. We see that Sn sits inside Rn plus 1, and so we might want to talk of submanifolds. This can be achieved. We define submanifolds via, again, going back to the Euclidean case and noticing that, well, I have copies of Rd inside Rd prime whenever d prime is greater than d. So for example, I have a copy of R2 and R3 just by setting all the coordinates except the first d to 0. And so in general, if I have some manifolds n and m, and the underlying set of n is in M, then in order to call n a submanifold of M and one speaks of an embedded submanifold of M, one really needs to put some conditions in the charts, because a priori these are just sets. Charts are all that gives them structure. And what we do, we suppose first of all that the dimension of n is not greater than m, and this might seem kind of unpleasant. It would be nice to derive this from the definition, but actually you can reformulate the definition where this is just something that follows, but that's just a more convenient way of writing it if we suppose that the dimension of n is not greater than that of m. And in addition to that, in order to say that n is a submanifold of m, we have to suppose that any point of n is contained in some chart of n, so here of B, this is what I call the smooth atlas. So yeah, here I've just wrote manifolds, but you can do this with any kind of manifolds, but although for us, let's do smooth manifolds. So again, in order for n to be a submanifold of M, an embedded submanifold, we need that any point of n is contained in some chart that we can view as kind of a restriction of a chart on M around P, in the sense that we can, well, a chart on N will be given by an open set, and some function from that open set, a projective function from that open set to a, it's an open set a posteriori, but really just some subset of our set M, or in this case N. So a chart on N around P is some subset U of N that contains P, and a projective function from U to some open subset of R dN, the dimension of N. And in order to extend that to a chart of M, we ideally would wish to find an open subset of M which intersects N in our open subset U, and find a function from that open subset of M to RDM, such that when we intersect the open subset in RDM corresponding to that map on our chart in M, the coordinate maps, we get that of N. It sounds a bit convoluted if I say that all like this, but really, again, the intuition here is you take the canonical inclusion RDN into RDM, where DM is no less than DN, and you just say that, well, we want that to have on our charts. On at least one chart or at every point of n, we need it to resemble this inclusion when we compare it with a chart of M. And this way we get a notion of an embedded submanifold. Again, this is sort of what I meant at the beginning of this talk. Really to write out the details, it becomes rather technical, but the intuition, at least one that's sufficient to work with these notions, is pretty clear. You just kind of have this inclusions of a linear subspace into RDM, and that's what models embedded submanifolds. At least what we can use to model submanifolds. So we can, something I've been consistently accidentally saying, induce a notion of an open subset on any manifold just by saying that, well, we have our atlas, and the atlas has local parameterizations. These are supposed to be bijections with open subsets of Euclidean space. Well, we'll just say that the images are open subsets, and images of open subsets of the domains are open subsets. So we just kind of import all of that. And actually, this defines topology in our manifold, but again, all that really means is we have a notion of open subset manifolds. And so the reason I mentioned this is because this gives us a nice way of obtaining examples of submanifolds. Now, we have an open subset of a manifold. I can give it the following atlas. For any point of this open subset P, and for any chart V phi of M around P, consider the chart where I intersect our open subset with V and restrict the coordinate maps. And you can verify, because these inclusions work well with smooth maps, that this is indeed a smooth manifold. An embedded, yeah, so well, the atlas gives us a smooth manifold, and together we get an embedded smooth manifold. And actually, you don't really need smoothness here to get this example, because as one of the conditions in our pseudogroup definition, any restriction of an class P map has to be class P, and here we're really just restricting from V to U intersected V, so it should work. I mean, not literally, because we are in the manifold, not in Euclidean space, but we just apply bijections, and so it works out. So one more pragmatic example we get out of this is, if you think about matrices and think about invertible matrices, then the invertible matrices form an open subset of all matrices. So we fix some n by n, some size. The way to see this is by topology. We can notice that being invertible is the same as having determinant not equal to 0. And this is kind of a condition that asks things locally, because it's just an inequality, a strict inequality. Or, well, if you want to put it in more abstract terms, the invertible matrices are the preimage of an open subset on the continuous map determinant. Determinant can be seen continuous because it is just a polynomial. And you could verify, of course, that if you use the standard chart on Rn squared, one I gave earlier, then the open sets we get are the same. I mean, it makes sense because the chart only has one local parameterization, the identity map, and so the images of the open sets in Rn squared, in this case, under the identity map will be the open subsets of Rn squared as a manifold, and this will be just the same because we just applying the identity map. So this gives us one of our desired, at the beginning of the talk, spaces as something to work with. I mean, I've not developed any theory of smooth manifolds yet, but we at least have this as a smooth manifold shown now. So ideally, of course, we would wish to have a little less trivial examples than Gillen R, because, well, really, Gillen R, it's still very much Rn squared. Open subsets of Rn squared is still just open subsets of Rn squared, so this is not that much different than just working Rn squared. Still fairly classical theory. Ideally, we would want to work with something like SL in R as a analytical option, because this is no longer an open subset of Rn squared. It is a closed subset, meaning that this complement is open. And this can indeed be argued to be an embedded submanifold in a similar fashion, except we no longer can just rely on continuity. We have to use the smoothness somehow. And we'll get to that near the end of the talk. It's a bit technical to, I mean, it's technical to argue, but to get there, we need to introduce some notions that we need to do technically. So, because the determinant is a function, of course, in this case, we have to regard properties of functions between manifolds in a differential geometric way. And that motivates the notion of, or at least it motivates our investigation of smooth maps between smooth manifolds. Well, of course, it's a very useful thing to consider either way. because functions between objects one can guess about is really, I mean, that's the whole point of category theory. If you have some class of objects, to map between them. But in this case, we can also use this to determine a bunch of things to be submanifolds. So that's useful. So what is a smooth map between two smooth manifolds? Well, of course, we want to have some sort of function underlying sets on the points. And the condition we give is really, again, something we can do locally. Because, well, again, in Euclidean space, a smooth function from one open subset of Euclidean space to another is smooth exactly when it's smooth locally. That was really the motivating example in the beginning, the remark that started our way of viewing smooth manifolds. And so if I have some manifold M, really I should know how to, or I guess N as our, M and N as our domain in this case, we should know how to think about differentiability or smoothness for functions out of N if you just think about them being smooth on every chart. Now, to be smooth on a chart, we identified the chart, the underlying set of it, with an open subset of Euclidean space by using the coordinate map. Or in the other direction, we used local parameterization. So really the definition turns out to be, if we have a function from N to M, both smooth manifolds, then it is smooth if whenever given charts u phi in N and v psi in M, then I can consider this function. I start in the open subset corresponding to U. Then I go via the local parameterization to N. Then I apply F. And I'm doing this only on the preimage of V. So I land with F inside V. And then I apply psi to land back in the Euclidean space. In this composition, it's a map from phi U to psi V. It is a map between subsets of Euclidean space, open subsets of Euclidean space. And so for that, it makes sense to ask for it to be smooth classically. So just have infinitely many derivatives via the limit definition. So this way we can import smoothness. And really here, this is where the pseudo-group approach kind of breaks down, and you need to require pseudo-monoids because we have a function between two sets that needn't be a bijection. You can have a smooth map that's not a bijection. And we really care about these maps. Pseudo-groups really suffice only to talk about anything pertaining to symmetries. But, well, for differential geometry on large, we care about also just any smooth maps. So, for example, constant maps, which of course aren't bijective unless one of the spaces involved is a point, which can also be checked to be a smooth manifold, just R0. So that's that. Now with smoothness, just like with manifolds themselves, it is really sufficient to work with any given atlas, not necessarily a maximal one. It is a fairly straightforward exercise using the definition of compatibility, smooth compatibility, that if you have one atlas on N and one on M, such that a map from N to M is smooth via this definition where you use charts of these atlases, then for any extension of these atlases, any two extensions, the map will be smooth with respect to them also. And so really when verifying that the map between manifolds is smooth in practice, it suffices to just consider one atlas. If I'm working with a circle, I don't have to consider all the possible charts compatible with the 4 I specified. It just suffices to consider the 4. So that's kind of the pragmatic way of verifying smoothness. Just pick one chart. And also it's pretty straightforward to verify that the composition of two smooth maps is smooth. All that really does is this middle term in our composition definition of smoothness is now replaced by composition of maps. It doesn't really change anything because that's how conjugation works. You can work out the details. Again, very many things to just write down and work out with. Well, that's how all the things are in math. Ultimately, the intuition is fairly simple. You do something smoothly, that's just like the Euclidean case. If you do smooth things and do smooth things again, in total you've done something smooth. And, well, you will require the fact that it holds in the Euclidean case to prove the general smooth manifold case. You can bring it back, because then in the middle term here in the composition you have a composition of smooth functions. Classically smooth. Okay, so to some examples, some more examples. Really, a lot of this talk I want to give examples because it will be really helpful for the spin geometry part of the book. Well, for the whole book itself. If you have two manifolds, we can form the product. And we can do this simply by taking the Cartesian product of the underlying sets and by setting charts, sort of products of charts. So if I have subset U of M and V of N, I can have a subset U Cartesian product V of M times N, the Cartesian product of M and N. And if I also have coordinate maps phi and U and psi and V, then I can extend these to U cross V just by mapping UV to phi U psi V. And this is kind of completely separated out into a phi part and psi part, so it remains bijective. And you can verify that P compatibility in M and N, so in the atlases A and B, translate over to P compatibility in this new atlas C. And this way we get a coordinate map of the U times V to phi U times psi V. And this way we get a P atlas on M cross N. So not again, this is not a maximal P atlas, not a maximal smooth atlas, but this suffices because we can extend any smooth atlas to a unique maximal one containing it. And well, immediately we notice that the dimension of the product of two manifolds is sum of the dimensions. Why? Well, because the dimension of a manifold we just find just simply as the dimension of the pseudo group that we are talking about. So the dimension of the open subsets of Euclidean space that we are identifying with subsets of our manifold. And well, if U is of dimension DMM, so I mean inside R DMM, and V of DMN, then U cross V as a subset of R DMM times R DMN is inside R DMM plus DMN. So is of dimension M plus DMN. Just we get this formula. And we can, as an example of smooth maps, verify that the projections are smooth. Again, this is fairly straightforward, again, kind of diagram chasing, where we do all the compositions and verify that indeed it turns out to be smooth. So another thing we can do with smooth maps is introduce the notion of two manifolds being kind of the same or isomorphic, really. I mean, if you're familiar with category theory, this definition of products is one version of direct products in the category of smooth manifolds and smooth maps. And this notion of isomorphism, sort of the equivalence, the smooth manifold equality of two smooth manifolds. If two smooth manifolds admit smooth bijections both ways, which are mutually inverse, then these smooth bijections we refer to as diffeomorphisms, and we call them diffeomorphic. So all the charts establish diffeomorphisms between the underlying sets of the charts and the corresponding sets in Euclidean space. And this way we kind of can identify smooth manifolds that differ in no significant, at least no analytically significant ways, because anything concerning smoothness regarding them can be translated between them just by composing with a diffeomorphism. So one example where this applies is with the graph construction. And now, given the product of two manifolds, we can consider graphs of smooth maps between any smooth manifolds. Because if I have a smooth map between a smooth manifold M and N, so from M to N, I mean, then its graph will lie inside M cross N, the Cartesian product, or we can interpret this product of manifolds, the product manifold. Again, just the set of all points x f of x, where x is in M, in the domain of F. And on this we can give the atlas where we take some point P f of P in the graph, and we just kind of use the atlas around P on M. So we take some chart around P U phi, and we pull it back up to the graph. And in this choice of atlas, we essentially make sure that the projection onto M from the graph is a diffeomorphism. So the graph we get of a function M to N is going to be diffeomorphic to M. I mean, it intuitively makes sense if you think of, say, a parabola. It's the graph of the map x mapped to x squared, R to R. And really, as a smooth manifold, it's diffeomorphic to R. You can just project down. That's really what's happening here. Really, the only thing we have to worry about is which atlas we put on the graph. And that's really where all the structure comes from, which ensures us that this gives us a diffeomorphism. So this is also an example of what's called an embedding. When we have the notion of being equivalent, isomorphic, and have a notion of being inside of something. We can say that something is isomorphic to something inside something else. So if a manifold is diffeomorphic to an embedded submanifold of another manifold, then we call the former manifold embeddable, or see that it embeds into the latter manifold. And such a diffeomorphism to a submanifold one refers to as an embedding. So that really allows later to classify alternative manifolds in a nice way, but we'll get to that. Before that, I want to move on with investigations of smooth maps, because, well, we want to show, so our kind of motivation for this part of the talk, that the special linear group is a smooth manifold. And in fact, using the techniques we'll develop here, we will show that a lot of other groups are, a lot of other spaces are smooth manifolds. And in order to do that, we really have to talk about differentiation of smooth maps. That's something we can do in classical analysis between, or form maps between open subsets for n. And we can try to translate that over to our differential geometric situation with smooth manifolds. And really, the many approaches of doing this, ultimately, we need, however, the derivative of a map to have some sort of value. And if we think about it intuitively, it should capture some sort of tangency. So we need to define the notion of a tangent vector. Tangent vectors can sort of be thought of as velocities. And so we can attempt to define them in terms of equivalent classes of curves, where we think of a curve in a smooth manifold as any map which kind of traces out the movement of a particle. So curve not in the sense of a smooth manifold of dimension 1 abstractly, but specifically one that's embedded, or just one that maps smoothly into our manifold. So the formal definition is as follows. And I said there are many variants, but this is one that's quite accessible. So let's say we have some smooth manifold M and some point P of M. Then if we have two smooth maps from R to M, which both map 0 to P, this is just for convenience, then we will say that they have the same derivative. So this is kind of what we're defining here. The same derivative at P, or at 0 you should say, but well, they'll define the same derivative at P. Provided if I take any chart around P, then if I compose the coordinate maps with the two curves, which will define as maps from R to the open subset of Euclidean space corresponding to our unlength set of the chart, then these maps will have the same first partial derivatives. So the first partial derivative, so the partial derivative with respect to one variable, any single one. So the maps are R to phi u, where phi is our coordinate maps and u is our unlength set of the chart. So this clearly defines the equivalence relation, because, well, if I have that, this is a function. This is so that the map which takes a curve and maps the derivative of this composition at 0 is a function, and this equivalence relation just says that two things are equivalent if they have the same value in their function. This is always an equivalence relation. Sometimes it's called the kernel of the function in algebra, is something that happens in algebra. And then we can just define a tangent vector as an equivalence class of this equivalence relation. So just an equivalence class of curves, all the curves through P that map 0 to P. By a curve in this case, I mean, again, not the abstract one-dimensional smooth manifold, I mean a smooth map from R to M, such that they all have the same derivative in this sense, one composition with any chart. And then we get the set of all tangent vectors, which we refer to as the tangent space, TPM, with or without parentheses. So in fact, one can verify that tangent space is a vector space. Clearly, you can scale up velocities, because, well, if you scale your curve inside by some factor, then upon differentiation, the factor will come outside. And so you can, given any curve, any curve that goes through P, get one which is kind of a multiple of it in TPM up to this equivalence. And more generally, you can verify that you can actually take linear combinations of curves. What this means is that the corresponding derivatives will be in corresponding linear combination. And this gives us a tangent space structure on or sorry, a vector space structure on the tangent space. And again, I'm skipping over some details here, but really it's not that difficult for verification. You can find it in many standard differential geometry books, which I'll also reference at the end of the talk. You just kind of verify the existence of the map, and this way you can combine um, tangent vectors in any linear combination, giving us this vector space structure, which makes sense. Well, if you think of tangent vectors as velocities, as we've defined them as, given any two velocities, you can kind of combine them in any linear combination and get a new velocity. You can scale them, you can add them. Now, something that comes with this notion of tangent vector immediately is what we wanted. It's the notion of a derivative, a differential of a smooth map. And the way that's defined is that we think of a smooth map as differential as something which carries the tangent vectors of the domain at the point where we're taking differential at, two tangent vectors of the codomain at the value of the function at the point. And all we really do, let's say we have some curve alpha in M that maps 0 to P. Well, if I compose alpha with F, then I first do alpha and then I do F. And so it's now a curve inside N, the codomain of F, which at 0 goes through FP. And this way I can take any curve inside M and reinterpret it inside the codomain of Fn. And by taking equivalence classes, verified that this indeed gives us a well-defined map. In fact, a linear map. Again, some stuff that needs to be checked, but if I would slow down to verify all of these details, that would be quite long. It's pretty standard stuff. And actually, it makes a lot of good exercises to verify these details. Make sure that this really is a linear map, and that this is well-defined. The reason this is well-defined is, of course, that we've assumed that map is smooth. And really, it would suffice to assume that the map is C1 again. Anything that makes sense for C1 manifolds makes sense for smooth manifold, because any smooth manifold is a C1 manifold. So C1 manifold being a manifold with respect to the C1 pseudogroup. But it's actually very useful, because now derivatives of functions are linear maps between vector spaces, and anything we can do between linear maps of vector space we can do with our maps. But before turning to that, actually a useful remark also is the structure of the tangent space. Again, something you kind of have to verify, but if you have any chart at the point, and let's say it's centered at the point, which means that it maps the point to 0, then if I take all the images of curves going through the axis of RD, where D is the dimension of the manifold, and I map those on the local parameterization onto the local parameterization of the chart into a manifold, then, well, viewing all these axes as our curves, we translate over to our manifold, and we get a bunch of curves there. If we take their equivalence classes in the tangent space, we actually get a basis of the tangent space. And so because we had the axis with the dimension of our manifold, it turns out that the dimension of the tangent space, a real vector space, is equal to the dimension of the manifold. A quite useful fact. So this way we can kind of get some numbers going to get an explicit basis of a tangent space of manifold to the point. And as mentioned, this allows us to, well, not just characterizing specifically, but just having these linear maps and the whole linearization. I mean, this is the linearization of analysis that I talked about at the beginning of the talk. This allows us to introduce a lot of notions for smooth maps. Namely, we can talk about the differential of a map at the point being surjective or injective, or generally talk about its rank. So the rank being the dimension of its image. If the differential of a smooth map at a point is surjective, then we call the point a regular point of the smooth map. And otherwise we call it a critical point if it's not surjective. So note that being surjective in this case means that the rank of this map equals the dimension of the codomain, so the dimension of n. We also refer to the map as submersion if it's surjective everywhere, this differential. And if it's injective everywhere, we refer to it as an immersion. So in the definition of a submanifold, we make sure to refer to it as an embedded submanifold. At least sometimes it depends on how much you care about differentiating or how often the other notions of submanifolds come about. But this other notion of submanifolds that people often care about are immersed submanifolds. And really what that is just any smooth map, so an immersion of a submanifold. So an immersion of a manifold into another is any smooth map that's an immersion. So anything that kind of injectively maps velocities in one into the other. This you can verify this means that it's locally an embedding, so locally a diffeomorphism. So around any point you have an open set on which restricting it gives you a diffeomorphism. But it's not not. You can look up very exciting examples of immuosed surfaces in R3 online, and I'll give an example later that I won't explicitly describe it, but you can have this other notion of submanifolds where you just locally embed it, not globally. And locally translates to onto the tangent spaces, because you can view things as local in terms of linear matters, in terms of vector spaces, the tangent spaces. So let's look at an explicit example. I kind of want to include this here because these sort of calculations are kind of the heart of what makes these things work, or at least what makes them useful. And well, there will be often situations where thinking about differentiating math like this in, say, spin geometry is quite relevant. So let's consider 2x2 matrices, real 2x2 matrices, and they form a smooth 4-manifold, where as my coordinate maps, I can consider this. Instead of taking the identity, I can translate the identity by some fixed matrix. And let's consider the tangent space of 2x2 matrices at this fixed matrix. So really, we're considering 4-dimensional Euclidean space and some fixed matrix. And of course, again, this is classical analysis, but I think it makes it easier to go for this example without having to worry about all of the maps, because well, we have one map to worry about. This is this translation. That's essentially that. So as we've seen, the basis for the tangent space will be images, or one basis for the tangent space, I should say, will be induced from this chart by taking images of the coordinates axis under this map, A plus identity on the matrices. So actually, I mean, it should be the inverse of that map. It should be the identities minus A, but it doesn't really matter after symmetries, because if you have that alpha of t is if I have alpha I of t for I from 1 to n as a basis, and alpha I of negative t from 1 to n will be a basis, because you're really just scaling the map by -1, the way that the derivatives work by the chain rule. So what will the induced basis from this chart look like? Well, it will be, you take some axis, so in this case it does still mean one of the components of the matrix, and you consider the curve that goes through the axis, so just kind of fixed, it maps t to t on the axis, and then you use local parameterization. So you add A to that, or in this case the matrix. And this is what it looks like. You have some x and y, which is the kind of labeling of your base vectors, some numbers, either 1 or 2. And then you fix all the components but one, and in the one component you shift by t. And then you take the inference of that. These are curves based at A, in the sense that they map 0 to A, and they will form a basis. So explicitly, you can look down below here. Use my cursor again. This is p mapping to this, and will be one of the representatives of the base element of the tangent space. So the reason we might want to consider this is if we say we want to take the derivative of the determinant. Again, the determinant is just a purely classical map in the sense that it is R4 to R in this case, but we can see how this works out in our terminology. So in order to take the differential of the determinant, we have to also fix, at least in order to get that in some explicit basis, we have to fix the basis of the tangent space of the codomain and the determinant of A, and we'll just take the identity in R. This is a curve that goes through, well, actually, sorry, this is a typo. This should be also shifted by A. That's my bad. But we can just take some curve that goes through A. Essentially, is if we shift, because we're differentiating, any shifts go away. So we can shift identity to the determinant of A and get this representative of the tangent space of the reals at A. Now, if we want to compute the differential of the determinant at our matrix A in these two bases, so I mean, using these two bases as a matrix, we have to, well, compute the value of the differential of the determinant at all of the base elements. So all of these four maps, T maps to Aij plus Kronecker delta Ix, Kronecker delta Yj T. And by definition, the value of the differential determinant will be the derivative of the composition of the determinant of the map. So this looks like this. For example, for x equals y equals 1, and you just do the explicit computation, this is just partial differentiation. So really, we just recover partial differentiation. And so in this case, we get this matrix D minus C minus B A. And in general, you can do the same computation. And if you're partially differentiating the determinant, you can kind of think about its multilinear properties. You will notice that you will get -1 to some power times the corresponding minor of the coordinate the component you're differentiating with respect to. And so in this case, you get this, and for say this to be not of rank 1, so not surjective onto the tangent space of the reals, you would need to have that the matrix is 0, so rank 0. In general, if we do the same computation in Rn times n, where we consider these minors, we notice that in order for a matrix to be a critical point, it needs to have rank no greater n minus 2. And so in particular, we notice that if you consider just the invertible matrices, we get a submersion onto the non-zero reals. And so that's rather useful because one way one can apply these properties of differentials of maps is via a theorem called the regular level set theorem. I mean, there are various ways of calling it. But this theorem, it guarantees us a way of connecting local properties of a map with globally extracting a submanifold. And it might seem like a rather complicated proof theorem, but actually it follows quite straightforwardly. Again, the details you can either work out yourself or find in a number of books. But if I have some smooth map manifolds at some point in the codomain, then I can consider this sort of level set at the point. And long as inside this level set there are no critical points of the map, then this is going to be an embedded submanifold. And in a sense, because we've specified kind of, you can intuitively think about specifying the dimension of n equations by taking this pre-image. We've reduced the dimension of m by this dimension of n when we consider this level set. And so the theorem states that this level set is an embedded submanifold of m of the corresponding dimension, the dimension of m minus the dimension of n. This is a very useful, I think the standard way of verifying that most things are embedded submanifolds is via this theorem. You find some appropriate map and you check this. So in particular, the reason we went through the computation of the determinant, besides being a good example, is because using that we can check that the SL and R set is an embedded submanifold of GL and R. Why? Well, take the determinant on GL and R and consider, well, it's a map GL and R to R, or to R star R. We can take 1 inside R star, and if the determinant of something is, well, actually, on GL and R, we've already verified there are no critical points in the determinant, so we know that the pre-image of any non-zero real under the determinant inside GL and R, but that's just the same thing as inside matrices, because if the determinant is non-zero, then you're inside GL and R. That will be an embedded submanifold of GL and R of dimension, well, dimension of R less than the dimension of GL and R. The dimension of GL and R is n squared because it's an open subset of n by n matrices, and of R1. So we know that the SL and R is an n-1 dimensional embedded submanifold of GL and R via this theorem. Another example would be, let's say we want to consider orthogonal matrices, O and R. So these are matrices where xt, so the transpose of a matrix times itself equals 1. So actually you can consider this map, which maps GL and R to the space of all symmetric matrices, which you can verify that is just Rn times n plus 1/2, just kind of noticing that you can only care about all on the diagonal and above it, and everything else is freely determined from that when you take a symmetric matrix. So we can take this map from GL and R to symmetric matrices, and the reason I mentioned this way of viewing them is because this way we can do it as an n times n plus 1/2 dimensional manifold. And we consider mapping some matrix, some general matrix, to a transpose times itself plus it times its transpose. This sort of like a commutator, but you don't subtract, you add. And then you can verify that the pre-image of twice the identity matrix will be the orthogonal matrices Y, well, because if this is 2, then that would have is 1 to the identity matrix, and then, well, you can do the correct computation and verify. However, you can, again, compute the differential of this map, make sure everything is fine, and note that inside this level set there are no critical points. And in fact, this will be the case, and so you will know that the preimage, the orthogonal group, will be of a dimension of G on R minus the dimension of the symmetric matrices. So n squared minus n times n plus 1/2, so n times n minus 1/2. For the special orthogonal group, you can kind of think about the orthogonal group being made out of 2 copies of it. And because it's only a matter of a simple kind of translation, so to say, you can verify that it's the same dimension. So one, or I guess a pair of, a family of examples, lastly, I want to mention, it's called Grassmannian manifolds. You can also use the same methodology to verify the Dawson manifolds. So you start with Rn, and you consider all R-dimensional linear subspaces for n. Now you can think of these subspaces as trace R symmetric idempotent matrices, because that's precisely what characterizes the orthogonal projection onto the subspaces. And you can again formulate this as a level set of an appropriate map. And I'll leave this as an exercise, it's a nice thing to work out. And verify the dimension of this is R times n minus R, and it's an embedded submanifold of n by n matrices. Indeed of G on R, because it's how orthogonal, no, sorry, not of G on R, just of n by n matrices. It's precisely outside of G on R, outside, except when R is n. An important example of this is the Grassmannian manifold. It's called the projective n space, where n is 1 less than the exponent of R we input into this construction. So real projective n space is the space of all lines through the origin in Rn plus 1. And well, by this dimension formula, we verify that this is n times 1 times n minus 1, so just n minus 1, so 1 less than n. So here, because our exponent is 1 higher, this just goes back to n, the projective n space being n-dimensional. You can also see it being n-dimensional by noticing that if you think of a line inside Rn plus 1, it intersects the n sphere precisely in 2 points. And so it's essentially kind of an SON ON situation. And this should be the same dimension as the sphere, which is n-dimensional. And indeed, you can verify that the one-dimensional real projective line, just a real projective line, is diffeomorphic with S1. No, the real projective plane is not embeddable in R3. Though here's an example you can look up. There are some nice animations. It's called Boy Surface. You can find an immersion of the projective real plane into R3. And so it's going to be local in embedding. And what it means for it to be an immersion is that all the differentials of the map at every given point are injective. So it's locally kind of fine when you consider the linearized situation. So lastly, I want to mention some general results about manifolds, namely some classification theorems. So first of all, the use of the notion of an embedding is that you can note the following theorem. It goes back to Whitney, and he proved that any smooth D manifold embeds into R2D. So in particular, say if I take the projective real plane, it does not embed into R3, which is not trivial to prove in and of itself, but it will embed into R4. You can find an embedding. Any curve, in particular note line R2. And in fact, you can prove that any curve is either a circle or the reals, as long as it's path connected. Path connected meaning that between any 2 points you have a curve, so a function from the unit interval to your manifold that's continuous, which maps 0 to the first point and 1 to the second. Again, you can talk about continuity because any C infinity manifold is a C0 manifold, because any C infinity map is C0. So another interesting theorem is the classification of compact smooth surfaces. A manifold is compact if it can be embedded in Euclidean space such that it is bounded and a closed subset so the complement is open. That's a very extrinsic characterization, kind of relying on this embedding theorem. There are more intrinsic characterization also, but they're a bit more technical. You can characterize compactness as any sequence having a convergent subsequence, in this case, not in any topological space. Or you can characterize compactness by any open cover having a finite subcover. So for any compact surface, you can prove, actually not that difficultly, by some combinatorial argument, by gluing polygons, that it either is diffeomorphic to the sphere, of course, or finite gluing along boundaries of disks, cutouts of disks, of the two torus, which is the product of the sphere itself. You can think you take one, as a circle of itself, you take one circle, and at any point you touch another circle, it's donut shape, and the real projective plane. And so this gluing is formally called a connected sum. So you're doing connected summation. It's a bit technical to prove that it works out. But this way you can get actually all the complex surfaces. So I don't think this result will be strictly necessary for the book, but I think it's kind of good to get a feeling of what these things behave like. Now, for higher dimensions, there are some. I mean, actually, there is a classification even of all surfaces, smooth surfaces, but it becomes very large. And then in 3 dimensions, it's really an intractable problem. I believe I'm not familiar with any neat results like this. I think there are some conjectures about some things about it, but it's really it becomes very large. So not really any classification. It's not even for compact free folds. So in that case, lastly, I'll give some references. I said there are many details. It's really not a overly comprehensive introduction to the subject. It's just kind of mentioning many of the notions, giving formal definitions you can think about yourself, and their basic behavior. But if you really want to familiarize yourself with things properly, you can see one of these references. They're all books I can recommend. Personally, I used the second one when learning differential geometry a few years ago. But actually, I think before taking this more modern abstract perspective, it might be helpful to think about it classically as manifolds being just, by definition, inside Rn, which is by Witten's theorem the same as doing it modernly. And that's the perspective took inside Pollack and Guluman's differential topology textbook, which is really a very elegant treatment of the subject, I would say. 2 takes a very modern subject, modern treatment, just kind of, well, doing pretty much what I did here, minus some. I mean, he doesn't talk about pseudo groups, but he does very similar approaches. He also defines tangent vectors differently. There are several equivalent definitions, but it doesn't really matter. You can prove that they are equivalent. And if you really want like a very proper fundamental treatment of the subject, there are 2 books by Kobayashi and Nomizu, Foundation of Differential Geometry, Volume 1, Volume 2. And I mean, really, like in the first 10 pages of the first volume, they cover everything that I've talked about here. So if you really want to either see a quick overview of these topics again or get into the things properly, you can look at that book. But I think if you're just interested in reading along this spin geometry book and aren't familiar with differential geometry as such, I hope this talk should be mostly sufficient given the 2 talks to come. So actually, yes, I did mention in the description to the talk, I'll talk about Riemannian geometry. And there are some more topics about differential geometry I want to talk about, such as tangent bundles. And next week I'll talk about vector bundles. And I've chosen to put Riemannian geometry and actually quadratic forms, which I planned to talk about last week, but didn't think of to include. So I'll include that next week in my talk about vector bundles. But hopefully, given this talk, my next talk about vector bundles and talk following that about leaf theory, you should be sufficiently equipped to follow along the reading, this understanding all the things the book talks about. So that'll be it. Thank you everyone for coming. This was a bit of a shorter talk this time. I hope it was fine. A bit tired this time. If any questions, maybe please share them now.
I think my question got answered.
Any others?
Which is on Lorentz manifolds, but then
Well, I mean, we'll get
Sabira
to that
and
next.
Theremin answered.
We'll get to that next week because that's a question regarding Riemannian pseudo-Riemannian metrics. At least, assuming you mean the same thing as Lorentzian manifolds. Okay, well, if there are no questions, let me stop the recording. Yeah, I don't know. Sorry, kind of been feeling kind of tired. I think this talk didn't